discontinuity, and function f is continuous at a number a if this limit is x approaches a of f(x) equals f of a. Some people split it up, some mathematicians, we can split it up into 3 parts. So you can say, so this has to satisfy, this can be written as 3 conditions, saying, first of all, that this exists, and then also f of a exists, and then they're equal. Okay, so of course, writing this down right there implies all 3 of these. Of course, they're equal, and then both sides have to be able to exist in order for them to be equal. Okay, and another way to think about it is you can, well, generally speaking, with a continuous function, you can write it without lifting the pencil from the paper, right, or the pen from the paper when you're doing the graph. That's kind of the technical. That's kind of the non-rigorous definition. But anyways, there's also, along with that, there's 2 kinds of discontinuities that we'll talk about. There's a third one, but we're not going to get into that. Okay, so maybe we will. Okay, so the first one is a removable discontinuity. And that's when you've got the graph coming like this, and then there's just a hole there. Okay, so you're coming along like this, and then there's just a hole there. And if you just redefine the function at just that one point, then you can make it continuous. That's removable. And then another type is jump discontinuity. I'll do another color. So jump discontinuity, and that's where the left and right hand limits exist, but they're not equal. So this is coming in like that, and that's going like that, and then these limits are not equal. So maybe they're both undefined there. Maybe they're defined at another point, or maybe they're not defined at all. So you come in this way, the left hand limit exists and the right hand limit exists, but they're not equal to each other. So that's a jump discontinuity. Okay, and then later on we'll look at something called the intermediate value theorem. And what that one says is basically, if you have, let's say you have a point of value, if you have a function that's continuous on an interval from a to b, okay, and so here's f of a, here's f of b, and it's continuous from here to here. And if you choose any value n, any value between here and here, so any of these values here, then there's going to be a value. So like there's going to be at least one value that one value c. There exists a number c in a to b such that f of c equals n. Okay. Okay, so that's the intermediate value theorem, and we'll come back to that later. We'll come back to all these ideas later. So that's just an introduction to what we're studying today. So let's get into the homework. So first of all, if f is continuous, what can you say about its graph? Okay, so the graph has a hole. That's wrong, because if it has a hole, that's a removable discontinuity. The graph has a jump, that's a jump discontinuity, which means it's not continuous. And the vertical, the graph has a vertical asymptote. That also means it's not continuous. So the answer to that one is just none of these, because any of these conditions implies discontinuity. Okay, so now we have a graph here, and we're supposed to determine for what values it's discontinuous, and whether it's continuous from the right, from the left, or neither. Okay, so here we have this smallest value here is this -4. Okay, it's not continuous there. And that's a removable discontinuity, and it's neither continuous from the left nor the right. because, yeah, the limit from the left and limit from the right exist, but they don't equal the value at the point. So that's not continuous from left or right. That's a removable discontinuity. Okay, next one is right here at 2, a -2. That one, as you come here, it goes, the function converges to 2. The limit is 2. And the function value is 2. So it's continuous from the left. And not from the right, because from the right it's going to 1, but the function value is 2, so that doesn't match up. Okay. Next we have, well, if you're looking at the graph, you might be wondering about this value here. It's actually continuous there, even though it's like a spike there. That's continuous still, because both the left and the right converge to 2, and the function values too. Okay, so 2 is the next place where it's not continuous, and this one's continuous from the right because it will go to that value at the right. So it's continuous from the right. Okay, and then the last one is 4. Looks like this might be a vertical asymptote going down there, but it is continuous from the right because it's going to 2 from the right. Okay, and that's the value at 4 is 2. That should work right there. Okay, so those should be the answers to that. Any questions about that? Okay, we'll move along then. Okay, so number 3, such the graph of a function f that is just defined and continuous except for a jump discontinuity at 5. Okay, so you want something that has a jump discontinuity at 5. So here, this is a removable. This is also a removable at 5. This is a jump discontinuity at 5. And this is a jump discontinuity at 5, right? Because here it jumps from there to there. The limit as you come in from the left is up here, is whatever value this is, maybe a 3. And the limit from the right is whatever value this is. It might be -3. But they're different. So both the right and left hand limits exist, but they're different. So that's a jump discontinuity. Okay, and then these ones are removable. So those are both out. Okay, and then we're supposed to have a removable discontinuity at 3, and this is removable right here. This is not removable. That's a jump discontinuity. This is removable. This is jump. So that's got to be the answer right there. That's the only one that's going to work. Okay, let's go to number 4. Use the definition of continuity and the properties of limits to show that, oh dang. Huh, I'm starting to do typos here. Okay, so this should be equal sign error. So this is what we're looking at right here. This function is continuous at a equals 1. Okay, so what that means, so what you want to prove is that this limit as v goes to 1 of 4 times the square root of 5 v squared plus 4 equals p of 1. Okay, so maybe we should find p of 1 first. Let's go ahead and do this right here. So this is going to be, so you plug in a 1 for v. And that's going to be 5 times 1 squared is 5, plus 4 is 9. So that's going to be 4 times 3, which is 12. Okay, so that's going to be 12. Okay, so now let's go to the tricky part where we're trying to justify each of these steps. So from here to here, we pulled this constant out to the front, right? And all this remained there. So that is the, this is the constant multiple law. Okay, now the next step, let's see, what do we do? This square root, we pulled it all the way out. Okay, we pulled this square root, we pulled that outside of the limit. Okay, and so that's the root law. Okay, then, let's see, what do we do next? Okay, so then this sum was split up into these two. So we took a sum and we split up into two limits. So that's the sum law. Okay, then, and then what we did, and then what they did was this 5 right here came out there. So that's the constant multiple law again. And then they evaluated this and they evaluated that. So this is direct substitution. Property. Okay, that's also direct substitution. And then, of course, that you just follow this logic and you get 12. Okay, so that's how you do number 4. Let's move along. Number 5, explain why the function is discontinuous at 3. Okay. So here, these are, when you have this piecewise defined functions like this, then the good candidates for where they're discontinuous are these boundary points, which is 3 is one of them. So we know f of 3 is 1. Okay, that's just from here. That gives us that. So the question is, the limit as x approaches 3 of f of x. The question is that going to be 1 as well? Or is that going to be something different? Or is it going to be undefined? So any 3 of those conditions will mean that that the limit doesn't that it's not continuous. Okay. So probably everybody is thinking, okay, let's we see this right here, and factoring is one of your favorite things to do. So let's factor like that. Okay. So I factor the numerator, and then there's like, these guys cancel, yay. And then there's nothing to stop us from just plugging in the 3, so substitution property. Okay, so I'm substituting in for here and here, I'm substituting 3s. And that is going to be 1/2 in the end. Okay, so the limit is 1/2, but the function value is 1. Okay, so 1/2 is not equal to 1. So that means that the limit as x approaches 3 of this is not equal to f of 3. Okay, so that means that that we're in this case right here where they're both defined, but they're not equal. Okay, let me see. this is not true because the left from the left and the right, they're both going to be 1/2. So the limits from the left and from the right and left are both 1/2. Let's see, f of 3 is defined, so that's not true. And then this does exist, so that's not true. Okay, so this could be the only answer. Okay, now, and then the next thing we want to do is sketch the graph. And what happens is this sort of thing right here is a good example of a removable discontinuity. And when you're able to cancel stuff up like this, and it just reduces down to this. So if we just now just try to graph the function x over x plus 3, then that will be a good indication. That will be the, and then just put a hole at x equals 3. Just put a hole in the graph there, and then redefine it to be 1 instead of being 1/2. Then that will do the trick. So this power and this power are the same, and so you've got a horizontal asymptote at y equals 1. Okay, and the reason for that, let me try to illustrate, is that you basically have 1 times that and 1 times that, so y equals 1 over 1. Okay, so it's 1. Because these are the highest order terms and they're both the same. So as x gets larger and larger and larger, it's going to go to 1. So you get a horizontal asymptote at y equals 1. You have a vertical asymptote at x equals -3 because of this right here. Okay, so when we go to graph this, okay, so at 1 we have this horizontal asymptote, and at -3 we've got a vertical asymptote. When x is 0, we get 0, so it goes through here. When x is 0, when you plug a 0 in, you get 0 over 3, so it goes to 0. Okay, and then so that means that we're going to come like this. And at 3, we're going to just have a hole in the graph. And this is going to go down, and then this is going to come up. This is going to go up like that, something like that. So this, oh, it has a hole. It has a hole here. That's true. But it's going to be defined right here because of this piece right here. F of 3 is 1. It's actually like defined right there on the horizontal, on the asymptote. And I guess this is lower. This should have been at 1/2. Whoa, this is really bad. Worst drawing ever. Oh well. Oh man, that's not much better. Oh well. Something like that. Okay, it looks, the Webassign exercise looks better. Okay. I think I made this too big. Oh well. Okay, number 6. Explain why m of x equals the square root of 1 plus 3 over x is continuous at every number in its domain. Okay, the textbook gives you a list of functions that are continuous everywhere in their domain. And polynomials are, so some examples of those would be polynomials, rational functions, exponential functions, composition of functions. But it turns out that pretty much anything you can write down in closed form is going to be continuous at every number in its domain. Okay, so that's the quantifier right there. So there are numbers here that are not in the domain of this function. So it's not saying it's continuous everywhere. It's just continuous at every number in its domain. Okay, so rational functions are, polynomials are. This is and then square roots are, powers are. So this is a composition of functions that are continuous in the domain. Okay, so the correct answer would be there. And then the second part is state the domain. Okay, so first of all, you can have a 0 in the denominator. So, okay, that's because of 3 over x. So whatever is here in this denominator can't be 0. So you're going to have to exclude 0 from the domain. Okay, that's first of all. Second of all, this 1 over 3x has to be greater than or equal to 0. It can't be negative because then we're taking the square root. Okay. So, so let's see. Let's try to figure this out. This is a little bit tricky, but I can sort of I can factor a 1 over x out of this. Okay, so essentially this expression and this expression are equal to each other. They're just equal to each other. And then I can argue this way. So I can split it up into 1 over x, and I can split it in x plus 3. It's a product now. And I'm looking, where is this product positive or non-negative? Okay, that's the question. And the two cutoff points are going to be -3 and 0, because at -3, this is 0, and at 0, this switches sign. So -3, this switches sign, and at 0, this switches sign. Okay, so this is negative, there, in this interval. Let's do that's the -3. This is going to be negative. Between -3 and 0, this is negative. But when x is greater than 0, 1 over x is positive. Okay, x plus 3 is negative here, and then positive there and there. Okay, so anything less than -3 is like -4, for example. If you take -4 plus 3, that's -1, which is negative. But if you have something greater than -3, like for example -2, you're taking -2 plus 3, that's +1. So it's positive, and it's positive over here as well. And so this product, 1 over x times x plus 3, you're taking a negative number times a negative number here, so that's positive. Here it's negative times positive, so that's negative. And then here it's positive times positive, so that's positive. Okay, so that means that the domain, okay, so this means positive or 0. So that means you're going to do this one and that one. Okay, but you're excluding 0 already because that makes this denominator 0. So 0 is excluded. -3 gets included as well. 0 is excluded, -3 is included. Okay, so your answer is going to be from negative infinity to -3. So including the -3. And then union, and then 0 to infinity, excluding the 0. And by the way, this symbol here, you can get that if you just type union. Okay, or you can get it from the menu on this side of Webassign. Okay, any questions about that? Okay, let's move on. Number 7, locate the discontinuities of the function f of x equals 3 over 1 plus 4 over x. And then graph the function. Okay, so here, again, this is an exponential function here. E to the x is exponential. 4 over x is rational. This 3 over something is rational. So this is a composition of functions that are continuous on their domain. So the answer would be everywhere. This is continuous everywhere except, well, everywhere on the domain. So it'd be everywhere except where it's not defined, which in this case is going to be x equals 0. So, so the discontinuity would be 0. Would be the only discontinuity, because that makes this denominator here 0, so that's undefined. Okay, and then graphing it. Oh, it says you can use a graphing calculator. Do we want to use a graphing calculator? Okay, yeah, I can show you how to do this on a graphing calculator. Okay, so so let's see, it's 3 over 1 plus 4 over x. Okay, so what I'm going to do is I'm going to go to GeoGebra.org. So that's the one, that's the graphing calculator that I'm going to use for this course. Come on. And start the calculator. And then just input the function. So it's 4 over, I guess I don't need that. So 1 plus e to the 4 over x. Okay, so notice as you put this in, it pretty much graphs it over here. And you can see that the answer is going to be the last one. Okay. So the answer is going to be the last one. Okay, so let's go back to the other one. And so it's going to look something like, so you know, yeah. So so it's going to look something like it's weird. So it comes like this, and then here it goes up like that. Something like that. Okay, so anyways, we'll move along to number 8. So use continuity to evaluate the limit. So again, this is going to be continuous everywhere because it's a composition of a square root function and a polynomial and another polynomial multiplied by a polynomial. So it basically means you can just plug the number, that you can just plug this 5 in for x to get the answer. Okay, so 5 times the square root of what, 34 minus 25, so that's 5 times the square root of 9. And square root of 9 is 3, so that's 15. Okay, number 9. Oh, I didn't put the instructions. So number 9 is, the question is what value of C makes F continuous? Okay, so what value of C makes F continuous? So when you have a piecewise defined function, you can remember continuity means that the limit is equal to the value at the point. And so for this, what's typically going to be a problem is if the left-hand limit and the right-hand limit are different. Okay, so what you're going to do is force the left-hand limit and the right-hand limit to be the same. So your limit as x approaches 3 from the left, and the limit as x approaches 3 from the right. So we're going to calculate each of those. Okay, so as you're coming from the left, you're coming through numbers that are less than 3. So it's this one here. Okay, so this is the formula that you want to use here. So that's the limit as x approaches 3 of c x squared plus 4x. Okay, and then meanwhile, this is when x is greater than 3. So that's the limit as x approaches 3 of x cubed minus cx. Okay, now again, here, this is continuous everywhere. It's a polynomial. So you can just plug the 3 in. Okay, so plugging a 3 in here gives you 9c plus, and then a 3 there gives you 12. And then the same thing over here, you can plug a 3 in here. So that's 27 minus 3x. Okay, so you set those equal to each other. 9c plus 12 equals 27 minus 3x. Okay, add the, no, not x. It's a c, 3c. Because your x is, because we're setting x equal to 3, not c, not 3 c equal to 3. Okay, so this 3 can come over here, so that makes that 12c. And then this 12 comes over here to make that, okay, 27 minus 12 is 15. Okay, so c is going to be 15 over 12. We can reduce that by a 3 to be 5 over 4. And this part right here also gives you the function value at 3. So plugging a 3 into here will give you the function value. So the answer is 5/4 anyways. Okay, any questions about that one? Okay, let's get on to number 10. Okay, number 10 says, use the intermediate value theorem to show that there is a root of the equation e to the x equals 4 minus 3x in the interval from 0 to 1. Okay, so a root would be a solution of this equation, something that makes it work. Okay, so to apply so if you have an equation like this and you want to apply the intermediate value theorem, then it's important you shift it over to being a function. Okay, so in other words, take this to the other side and then make this whole thing a function. So e to the x minus 4 plus 3x is a function. This is a function. Make that your f. So all of this is our f of x. And this equation is equivalent to setting this f of x equal to 0. Okay, so it's an exponential plus a polynomial, so it's continuous everywhere. So it's continuous on the interval from 0 to 1. Okay, now f of the left endpoint, 0, is going to be, so you plug a 0 into here, then you get e to the 0 minus 4 plus 3 times 0. That's 1 minus 4, that's negative 3, right? That's negative 3. Okay, and then you're going to calculate f of 1 by plugging a 1 in here. So that's e to the 1, or just e, minus 4 plus 3 times 1. So that's going to be e minus 1. Like that. And we know that, okay, so e is approximately 2.7 something. So e minus 1 is going to be 1.7 something, which is positive. So, and this is negative. Okay, so notice that this is negative, and this is positive. That's important right there. So this negative number, which is f of 0, is negative. F of 0 is negative. F of 1 is positive, so that goes here. So f of 0 here, f of 1 there. Okay, so by the intermediate value theorem, there's a number c such that f of c equals 0. Okay, and that gives it to you. So let me illustrate this so you can see what's going on. Let's see here. Okay, so here we have we'll say this is the y-axis right here, and f of 0 is -3, so you're down here. And we'll put 1 way over here. F of 1 is e minus 1, so that's up here. Okay, so we know that these 2 points are points on the graph of y equals f, or y equals e to the x minus 4 plus 3x. Okay, so we know that if we put in if you put in a 0, we get -3. If we put in a 1, we get e minus 1, right? So that's why we got these 2 points right there. Okay, now this function between here and here, at some point, it's got to cross this. Okay? So it's like you're playing soccer and this is the goal. This is like this is your goal right here. And so you're on this team over here and you kick the ball. And the referee wasn't watching though. But the referee wasn't watching, but you know, you have the ball right here, and then the next instant the ball's right here. This is the back of the net right here, right? And the ball's over here. And the referee says, I didn't see it cross the goal line. But then you're like, well, it had to cross the goal line, right? And I can prove it by the intermediate value theorem. And the referee goes, oh, you're right. There's no way it could have gotten to here without crossing this.